To get back to the source, you need the source address. Next task was tell the destination how to handle the packet. And here I want to go back to our protocol diagrams that we had and our different layering architecture that we had earlier. And remember now that when the packet arrives at the destination, it's coming in off the wire and it's traveling up this protocol stack. Okay? So now the packet has reached the destination. It is at the right IP destination. And so in your operating system, you've looked at the IP header and you said, great, I've reached the IP destination. What next? Remember that packet ultimately is being consumed by an application. What do I need? You need one of those, not the second. So I need at least the protocol number, something that identifies which protocol at L4 is going to process this packet. Right? So I received the packet at IP. I need to know, is this a TCP packet, in which case I'll send it to be processed by TCP? Or is it a UDP packet, in which case I would hand it to the UDP module? TCP and UDP we've not covered yet. That's our next topic. These are different layer 4 protocols. But I need to know which one the packet has to be sent to next. Does that make sense? Let me repeat it one more time. It indicates which protocol should handle the packet next. So it's a protocol field. Protocols are given a unique number by, again, the numbering agency ICANN or IANA, just like IP addresses and AS numbers. Different protocols will have a well-known protocol value. Okay, and your protocol field is going to carry that protocol value. And this is used at the receiving end to demultiplex where the packet should go next. Question? Yes, so the protocol field is going to be part of the IP header so that the IP layer knows where to send it next. So what does it mean to have a protocol field? So as I said, these protocols have well-known numbers. So for example, TCP is 6, UDP is 17. And so when in my IP header I say my protocol value is 6, what that means is that the next header is a TCP header. Okay, so it's telling me how to process the packet after IP. If I said it was 17, then it tells me that the next header I should expect is the UDP header. Any questions on this? Yeah.
And that next header is inside of the same packet.
Right. So let me go back to, great question. Let me go back to that very first diagram. Where's that? Right. So if you remember going down the stack, we added all these headers. And then when you reached the destination, at the IP layer, you received a packet and you took off the IP header and the next header inside was TCP and you passed it up. So this is saying I'm going to take off the IP header and now do I know where to send? Should I send it to TCP or should I send it to UDP? That's what the protocol value is telling us. Any other questions? Okay. So finally, getting responses back to the source, we covered this already. I need the source IP address. So taking stock, these are the fields we're going to need in the IP header so far. We had two more tasks we needed to do. One was to deal with problems along the way, and the other was the specialized handling. What problems do you think we could have in the network? I think one of them came up, which was I could have some corruption. Some of my bits get corrupted by the equipment along the way. Yeah. Some packets could be dropped. Why? What could I put in the IP header, though, to help to deal with this packet will get dropped? It's not a bad thought, but... So if we had error messages, then it would make sense to have something like send an error for this packet. That's not what the standard IP does. It doesn't necessarily send, most of the time doesn't send error messages, yeah.
Sequence number of a bunch of packets.
Say more. Why would you need sequence numbers?
It's probably more useful in highlighters, but if you have multiple different packets and you chunk up your data into different packets, you're not guaranteed that all of the packets will take the same route to the destination, and so you need to tell the end host how to piece back together in order
Okay, so you're right that we will eventually need some sequence numbers. We're going to do that at L4, not at L3, because the job of the network is not to guarantee that packets go in order, but we will need them when you got to another point that we'll get to in a bit. So you need some signature, or we're going to call it a checksum, not so much for tampering, but just to make sure that the bits you sent are the bits you received, for whatever reason. Anything else? Right, you don't want the packet to wander the network. And why would the packet wander the network? Because, as you remember when we were talking about routing, it takes some time for routing to converge, and you can have loops while we're waiting for the paths to converge. And so if you didn't have any mechanism, these packets would just be looping forever. So we're going to have something we call a time to live, and we're going to drop a packet if it's been going around in the network for too long. Great, I think you guys got all the... fragmentation was the other one. So let's go through these: loops, corruption, and fragmentation. So preventing loops, as I said, while we're waiting for routing to converge, it's possible that you have loops for a period of time. We don't want packets looping forever in the network. And so very simple solution, we put a time to live in the packet header field. At every hop, as the packet is being forwarded, we decrement the TTL. If the TTL ever hits 0, this is one time we could send an error message back to the source saying time exceeded. And you used this capability when you did traceroute.
In the project, we checked just like the current universal time. Is that not done because it's hard to standardize the same time?
Typically, you don't have synchronized clocks across routers, so you wouldn't do an actual time. There is work on clock synchronization, so maybe one day, but not yet. Right. So this is a little arbitrary. In this case, we send a message back to the host saying, hey, I dropped your packet, time exceeded. And routers don't always do that for security concerns, but it's true that in this case we designed to have error messages, but in other cases we don't. A little arbitrary. I don't think I have a good reason for that. Any other questions? Okay, so just one point to note: if you want to send an error message back to the source, this is another reason why we need the source address and why routers need the source address. Okay. Header corruption. Are people comfortable with the idea that bits can get corrupted along the way? Right. This comes down to, your signal at some level is an analog signal. And you look at the power, or you look at some signal strength, and you decide whether it's a bit 1 or 0. And sometimes if your laser flickered or something, a 0 could get flipped to a 1. And so there's physical characteristics of a link. There are reasons why you could corrupt bits or corrupt packets. So a checksum is just a compact fingerprint, or you can think of it as a hash, or there are lots of checksum algorithms out there that will summarize what the data being carried is. IP uses a particular form of checksum. The part 2 members, IP computes that checksum only over the IP header. Okay? And so if it's not correct, so every time a packet comes in, the router or the destination is going to check. It's going to compute the checksum over the header. It's going to compare it to the stored value of the checksum. If the two are not the same, it's just going to drop the packet. This means the checksum is updated at every router. This is a bit of a pain because it's a little expensive to compute a checksum. Why are we computing it at every router? Yeah. The TTL changed. Anytime I change any value in the header, I have to recompute the checksum. Why did we include the TTL in the header, in the checksum calculation? Why didn't we just say, I'm not going to include the TTL? Yeah, to protect the TTL, but that's not the best reason. A reasonable design could have been to say I'm going to leave out the TTL, but that's not what the earlier designers did. Why do we only compute checksums over the header? Because other bits could be corrupted as well.
This is not your problem at that layer, like you don't care what the content is, and let a layer handle that.
Yeah, so the early designers were like, the job of the network layer, it's a very purist thinking. L3 is to protect the L3 header. I'm only computing checksums over the L3 header. Why did we even need a checksum in the first place? Why did routers, sorry, let me rephrase that. Why do routers have to check? whether the packet is corrupted. What would happen if they didn't? Yeah? Yeah, so exactly that. The thinking was, well, what if I have a link that starts malfunctioning? Let me roll that back. What if a router did not check the checksum? What would happen? It would forward the packet on to the destination. The packet would reach the destination. The destination could check whether the packet is correct, whether the checksum is correct. And if it's not correct, it can drop the packet. So you should think about this, start thinking about the end-to-end principle. From a point of view of strictly correctness, it would have been fine to have not had routers compute checksums. Would have been good, in fact, a little less work for routers to do. And the end host could have checked whether the checksum was fine. You would have saved the destination from receiving bad data. So it would have worked fine. The thought was, well, we've wasted all this bandwidth for sending, corrupted data over the network. This is slightly, people don't worry about it as much anymore because they're more worried about scaling routers than they are about checksums. And so we'll get back to that. This is a decision the IPv4 designers made that was maybe not ideal. Last point on the problems. One of the things that can happen is this question of fragmentation. I think this has come up in earlier lectures where we said every link has a maximum transmission unit. This is the largest unit of data that link can carry. So sometimes a source might send a packet that is larger than some link's MTU. And so when the packet reaches that link, it is the job of the router at the front of that link to do what we call fragmentation, which is to take that packet and chunk it up into smaller packets. Okay, so if you had a large packet here, and let's say I was chunking it up into 1500, which is the typical Ethernet MTU, you would take that packet contents and chunk it up, in this case, into 3 independent packets, and you would create a new header for each of those fragments. And then ultimately, you would have to reassemble those fragments back into an original packet. So it's conceptually, it's a fairly easy thing to understand. Packet came in too large, I'm going to chunk it up and send out fragments, and then I'm going to reassemble it. It gets a little tricky and a little fun in exactly how you design fragmentation. So you're going to do this in section. Okay. Any questions on fragmentation, though, conceptually? Okay, so with that, we have added 3 more types of fields to our IP header. We have a TTL, the source address we already had, and we're going to have a set of fields to do fragmentation. There's a question somewhere that I, yeah.
I have a question about writing checksum. Wouldn't it also be beneficial because the destination source might have been corrupted, so you don't want to send it to the wrong destination?
Right. So what would happen if you sent it to the, that's a good question. If your destination bits were corrupted, but they still got you to some valid destination, would that destination accept it? Yes, you're right. That could be a problem. You'd have to have many things that go wrong because you would also have to have a process, an application with a port and that's sitting there. So, but in principle, yes, you could imagine that bad case. So the last thing in our header was this question of what if your packet wants some kind of special treatment? And there's 2 kinds of special treatment that the early designers of the internet considered. As you'll see, these fields have not worked out so well. But the first is, imagine that you don't want to treat all packets the same. You want to indicate some customers that are more important, higher priority, or traffic that is sensitive to delay or sensitive to throughput and so on. If you go back to our very first lectures, this was this idea that the internet should do more than just best effort traffic delivery. And then the second was the thought that maybe sometimes you want to do some kind of special functions or features treatment for the packet, like for diagnostics or debugging or other reasons. And so there was this entire class of fields called options that got introduced. Okay, so let's take the first of those. Type of service is exactly what it sounds like. It was originally designed to be a set of bits that would tell a router how to treat this packet. What kind of service does this packet want? Either, delay sensitive, throughput sensitive. Over the years, many people defined it and redefined it and tried to use it. It never really took off. The one use of these bits that has persisted is just for priorities. If you want to indicate different